Okay, so we're gonna so this algorithm. So we're gonna talk about an algorithm that forms a union of sets. And so this is actually in. If you look up the Sedgwick book, you look you type in his name, Sedgwick algorithms. It's actually in chapter 1 of his book. I think it's the last section in chapter 1, and there's 2 different versions of this algorithm. I mean, the result is the same, right? Because you can't have. I mean, the answer shouldn't depend on the algorithm, right? But the second version, which we'll talk about on Monday, is a little more sophisticated, and then I'll talk about something else on Monday too, just something more, just some review of the comparable interface, just some methods with comparable interface. So we can review that, and then this will be on the quiz on Wednesday, a week from tomorrow, next week's quiz, not today's quiz. And okay, so yeah, today's quiz, the quiz is just short. It's just all on heap sorts. Okay, so so this problem is about forming the union of sets. And so for our set, so I think we're all familiar with sets from our math courses, right? No, usually they're numbers, but they don't actually have to be numbers. If you took Math 265, you took form sets of other stuff. And you can think of like an array list is like a set, or an array is just a set. So it doesn't actually have to be numbers. But in this case, our sets will consist of numbers. Okay, so when would maybe this might be good, so useful. So let's say you have some, and I don't really know a lot about networks. Let's say you have a computer network. Here's some computer network. So these two here's like, so this first network, this network on the left can't talk to the network on the right. But let's say we just connect this computer up with this one right here. So now let's say computer B can talk to computer. So not only can computer B talk to computer C, so we connect computers A and B, B and C. Now there's a way for computer A to talk to all the way to computer E. Right? You go from A to B, B to C, C to D, and D to E. So when we connected the network. So basically what we did is we connect the networks containing computer B and computer C. And we're going to do something similar. We're going to form the union of sets. So let's say I might have a set containing 0 and 3. It doesn't look like a set, does it? And I might have a set containing, let's say, 4 and 8. And then I might say, okay, well, let's form the union of the set containing 3 and the set containing 8. And so so when you do that, you're getting 0 and 4 come along with it. So I'm forming the union of the set containing 3 and the set containing 8. And so we get one giant set. And that's kind of what we're going to be doing. With this algorithm. Again, we'll learn kind of today's method is kind of not that sophisticated, and the one we'll learn on Monday is more fun, meaning it's more fun means more harder, I guess. I don't know. Okay, so basically you should be able to describe the UnionFInd problem. So so we just did that's kind of the problem right there. Okay, so there's something called a quick find. In this case, actually I didn't emphasize this in the last class. So quick find means finding the set number for a given element. So we can quickly find, and then, but maybe the union is of order n. You'll see that the method, the code is really very short. And there's this one method that actually forms a union of 2 sets. It's of order n. So let's say you have n elements distributed over a bunch of sets. It's going to, every time you form the union of 2 sets, it's in order n. You have to do n comparisons, and but the finding is at order 1, which quickly it's very easy to find the set number. What set number is element 5, and we'll see that's an order 1 operation. Where this other algorithm, quick union, forming the union is an order 1 operation. So maybe the finding is and well, it turns out we'll see the finding is log of n. That's next week. Okay, so we already did this part. See how fast we're going? We're already on slide. This only took me like about a half an hour in the other class. So okay, so connected up, we can the computers in a set or elements of a set. So like here we think of, they're all A, B, and C are all in the same set. So let's say they're connected, and D and E are in the same set. So we'll say they're connected. Yeah, so if you form the set containing F and D, then F will be connected to, yeah, you form the unit set containing, let's say like F and D, F will also be connected to E. Okay, so there's actually code for this. So let's just look at a little bit of the, some of the, there's some of the, like the constructor. And I think I posted the code online. There's actually a files called Java code. In the file section, there's, I haven't put in the module yet, but if you go to the last, is it lecture 14 or something? The file, the number of in the files, the lecture number doesn't correspond to the module number, but it's the lecture with the highest number of files. Yeah, I put the Java code there. So we're gonna have a constructor. So we're gonna have n elements. So our elements are always, so if there's n elements, it's always gonna be they're always gonna start from 0, just like an array index. And it's conveniently done, so we can use the array indices. So if we have 10 elements, so if we're distributing 10 elements over a bunch of sets, the elements are gonna always be numbered 0 through 9. They always start at 0. And then there's this method called union. This means form the union of the set containing P and the set containing Q. Okay, this find, you really, as far as the code, there's actually a class called, this UnionFInd class doesn't really need this find. So let's say that, the client class wants to find a set number for a given element. But the find actually tells, would be the set number containing element P, right? And then count tells us the number of components. But the thing that's really going to be of interest to us are these first two, the constructor and the union. Okay, so we're just going to do quick find for right now. Okay, so let's just look at the constructor. So okay, so let's say let's say we have 5 elements to begin with. We're going to so the constructor would contain 5 sets, where each element is in a set with, element I is in set I. So initially, the constructor, again, if we had 5 sets, so 0 would be in set 0, like 1. Oh, my notation's terrible. Okay, so this would be in set 1. I won't write set every time. I think you get the idea. Okay, so maybe I shouldn't try writing this. So the second set would contain 2. That would be in set 2. And then the set containing 3 would be in set number 3. Okay, so initially, element I is input in set I. So let's actually, so the constructor contains n components with element K and component K. So here's actually the code for the constructor for this quick find. Okay, so what we're going to do, there's actually an instance variable, int. It's an array called ID. And what we do is, okay, so if we invoke the constructor with some positive integer n, so count tells us, so we initialize, yeah, and so there's also an instance variable called count. And that tells us the number of sets. So initially, count is equal to n. For every element is put in its own set. And ID, so we allocate memory for the ID array. So it's going to be an array of length n, so that's fixed. And so here's how we initialize the components. ID of k is assigned k. So the input is the element number. So the index is the element number, and ID of k is the set number. Yeah, so element k. When I say component, I guess I could have also, wherever you see component, you could also put set. I use those words, I guess, interchangeably. I know some students have gotten annoyed with me. Okay, but yeah, so element k is stored in component k or set k. So that's why it's quick find. Okay, what element? So what set number? What set number contains element k? You just look at the array value. So array is random access. So it's just an order 1 operation to get the set number for an element. Okay, so here's there is this method that, okay, so find the set number for element P. So the code itself doesn't really need this, but if the main method needs to know the set number, let's say you're writing code and you want to know the set number for a given element, you call the find method. So, okay, so it's the union method. This is the key part of the code for this algorithm. And also for the next version of this algorithm too, because isn't that what we're doing? We're trying to form the union of sets. Okay, so the union method forms a union of the component containing element P and the component containing element Q. Again, when I say component, that's just another way of saying set. Okay, so let's just look at this method here. Okay, so union of, so the input are element numbers. So we're putting in two element numbers. And students, I also notice I have to fix this. I noticed that there was a compiler error in here. There should be one more curly. Maybe I should just put it below. I guess it doesn't matter. But right. So this, yeah, I noticed that there was this didn't actually have a matching brace. So so this would go like that. Okay. Okay. So first we get this. So the PID is the set number or the component number for element P. QID is the set number for element Q. And if they're different, if P and Q are in different sets, what we do, and so here's forming the union is an order n operation, right? We're looping over the entire ID array, and the ID array is of length n, where n is the number of elements. So it's saying if the array value is equal to PID, we change it to QID. So basically, let's say PID was 3 and QID was 6, and let's say 5 was in. So let's say 5 was in set 3, or let's say 5 is in set 3. Let's say let's say 3 and 5 are in set 3, and 6 all alone is in set 6. So what would, okay, so what would happen is that if we, so in this case, yeah, so let's say we're doing union 5, 6. Okay, so let's say 5 is in set 3, so the PID is 3, 6 is in set 6, so the QID is 6. What we would do is we go through this array here. Oh, ID of 5 is 3. We're going to just change that to 6, right? So ID, what we do is it changes to 6. So now this would not be in 3. We would put it in set 6. I'm not sure if this visual is so useful, but I think when we do the worksheet, I'll help clear it up if you don't understand it now. And then you reduce the number of sets, but yeah, so if PID, so if elements P and elements are Q are in different sets, you form the union and then you reduce the number of sets by 1. And that's really all there is to this, students. Yeah, so the union operation is an order n operation, right? So finding a set number is just an order 1 operation. It's just the value of it's just an array value. So why don't we actually look at a problem here? And I think hopefully I think this first algorithm isn't that bad. Are there any questions right now? Okay. So I'm just going to do one problem. I'll let you do the other problem. Okay, so okay, so okay, so initially, so the input is the element number. So we have n, so we have 7 elements in this case. So I started 0. So initially, what it would look like 0 would just be in set 0. And I won't actually write them all, and then dot, 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 and then 6 would be in set 6. So initially, element I is in set I. Okay, so this is the initial, so the ID array gets set up in the constructor. So initially, ID of 0 is 0. an ID of 1 is 1. So in other words, element 1 is in set 1, element 2 is in set 2. Okay, so we haven't done anything yet. Okay, so when I go 2-3, that means, so 2-3 means this is union. So we're going to take the union of the set containing 2 and the union of the set containing 3. So anything that's in set 2 is now going to be moved into set 3. Okay, how do you know if you're in set 2? Well, if your ID number is 2, right? Because remember, that's what the code said here. Let's just go back quickly. Yeah, so you find the PID, you find the ID of, so in this case, we find the ID of 2 and the ID of 3 and get the, and then, to find out the set number. Okay, so in this case, now how do we get the set number? You just go back to the previous row. Oh, ID of 2 is in set 2, 3, ID of 3 is in set 3. You always go to the previous row and you hope that the previous row is correct. Okay, so if you didn't make any mistakes, it will be. So in this case, our PID is ID of 2. And so initially, the ID of K in this problem, I tried to make it so it kind of changes that right away, but initially the ID of I will be I, but it isn't always that case. And so, and the QID is ID of 3, which is 3. So now you go through this array, and isn't that what that loop would say? Oh, is ID of I equal to 2? If it is, you set it equal to 3. So basically, you're just going to copy this first row over, and wherever you see 2, you're going to be 3, and everything else stays the same. So 0, 1. Oh, here's a 2. So now that's a 3. It still stays 3. That's a 4. That's a 5, and that's a 6. Let's see if I can make a better 3 here. Marshall, okay. Okay, so now what would happen is, see, initially, let me just draw this set one time. In the solution file, I did do all the sets, and the type of solution. So initially, right, we had 2 in set 2 and 3 in set 3. But look what happened. ID of 2 is now 3, so set 2 actually went away. And what we get is 2 and 3 are in set 3. Because if you look at that row there, after 2, 3, you don't see a 2 in that row. There is no set 2 anymore. So after every union operation, if there's actually, if the elements are in different sets, one of the sets will go away. If the elements are in the same set, there's essentially no change. You basically don't do anything. So any questions about that? Oh, hi, Dominic. So, okay, so let's just finish this problem here. Okay, so now we're going to do, so now we're going to take the union of the set containing 0 and the union of the set containing 4. So once again, okay, what's the PID number for 0? Oh, you just go to the previous row. It's 0, right? Let me just do one more of these. So in this case, yeah, the PID number is 0, and the QID number is, well, we just go to the previous row for 4. Oh, ID of 4 is 4. Okay, so all the zeros will change to 4. So now let's look at that row there. So our last row, ID of 0 is 4, and ID of 4. That means that 0 and 4 are both in set 4. And I remember I used to encourage students to draw the pictures, and no one ever really did. Okay, but okay, so let's do one more here. Let's do the whole thing, but let's do one more. I'll find the PID. Here's where it's different, students. And so did I? Oh, shoot, ID. This should be 3. That's better. Okay, so now we're going to form the union of the set containing 2. It's this one right here, and the set containing 5. And now what's going to happen is okay, what's ID? What's PID? What's ID of 2? So now this is where it's a little bit different, and so you go to the previous row, and so now the PID is not 2, but it's 3. And the QID, well, we go to column 5 in the previous row, and it's still 5. So now all the 3's change to 5. See, so now we're actually going to change two values. So when we formed the union of the set containing 2 and the union of the set containing 5, the 3 went along with it because 2 and 3 were in the C. 2 and 3 were in the same set. So 2 and 3 are now both in set 5. It's pretty wild, students. Oh, so here's another fun one. Okay, so this one right here. And then, so now we're going to form the union of the set containing 0 and the union of the set containing 1. Again, you go to the previous row. Well, 0 is in what, set 4, and 1 is in set 1. Okay, so all the 4s, anywhere you see a 4, you change it to 1. So the PID is 4. So wherever you see and the QID is 1. So wherever you see a 4, you put a 1. 1, 1. Yeah, wherever you see a 4, you put a 1. So now, so wherever you see a 4, so now 0, 1, and so 0, 1, and 4 are all in set 1 now. Yeah, 0, 1, so 0, so go to column 0 is a 1, column 1 is a 1, column 4 is a 1. So elements 0, 1, and 4 are in set 1. There's 3 sets left, right? Because if you look at this last row, you see 1, and you see a 5, and you see a 6. Right, because every time you form the union of set, one of the sets goes away. Okay, so now let's look at this one. Form the union of 5, 3. Oh, but what's the PID for 5? Yeah, so the number on the left can be larger, it doesn't really matter. Well, the PID for 5 is 5, and the QID and 3 is is set 5. They're both in the same set. So we don't do anything. We don't actually decrease the number of sets. So we just repeat the previous row. And now the very last one, and then I'll show you the type solution. ID after 6, 2. Okay, so we're going to take everything that's in set 6 and put it in the set containing 2. Well, okay, so let's see, what do we have? So the set containing 2, so 2 is in set 5, right? So what do we have? So we have 2, 3, and 5 in set 5, and 6 is in set 6. Okay, so the PID for 2 is at, no, the Q, oh, I'm sorry. Yeah, set 5, so this is set 6, hello. No, 6 is on the left, so the PID is 6. And the QID, so 2 is, so we go to column 2, we see a 5 here, is 5. So all the 6s turn into 5s. So there's 2 sets left. The set numbers, I'm saying, don't really matter. It's the actual contents of the set itself. So why don't we look at the type solution, because this is kind of a mess. And see, and so there, yeah, so you see at the end, here, so the set containing 1 contains a 0, 1, and a 4. And set 5 contains 2, 3, 5, and 6. Yeah, so you see here, you see the initial component, 0 is in set 0. And yeah, so the number to the left of the colon is the set number, and then to the right is the actual contents of the set. So that's all there is. I thought maybe if you want over the weekend or when you're practicing, that there's actually another problem. I can actually put up some old quizzes too. Here's another problem. So I'll put up an old quiz too for you to practice on. That's pretty much, I mean, I can do the second problem. It's pretty much the same thing. So I'll let everyone try that for itself. We can review one more problem on Monday. But are there any questions right now on this quick find algorithm? Again, it's finding the set number is fast, right? Finding this, that's what we call quick find. We can quickly find the set number for an element. We just look at it, it's just an array access. And but the union is order n. It takes we have to loop over an entire array. Yes, we have to loop over this entire array to form the union. And again, and then the algorithm we'll learn on Monday is forming the union is just changing one array value. So the union will be order 1. and find, and we'll learn that the find is order log of n, which we won't prove because I think it's proof by induction. But any questions right now? So
I got a quick
go ahead,
question.
Devin, go ahead.
I was curious, can you use different things besides numbers as well in this example? Like, can it be objects or?
Well, the thing is, yeah, I
characters?
think you could, but you'd probably map them to numbers. I think it's somewhere you're going to map them to numbers because the thing that makes this work is that the element number can be used as an index to an array.
Okay.
So yeah, so you could, but I think somehow you just have to have some kind of map, like like per, you know. So yeah, so you just do all of this, and but yeah. So let's say if you array of person objects. So when you like when you go like union 2, 3, it just means you're taking person 2 and person 3 from the array. But so you'd actually form these sets, and then you can actually then form the so when you get a set like this, let's say you get a solution like this, like 0, 1, and 4, you know that 0 means like person 0 and person 1 and person 4. Does that help?
Yes. Thank you.
Because yeah. So because if you don't use the array, if you don't use numbers like 0 through n minus 1, you're gonna have to rewrite the code. So yeah, that's what makes it kind of that's the advantage of using 0 through n minus 1. The element numbers can just be used as an array index. So, but it's a good question. Anybody else?
Yeah, I just have a question on the heap sort code.
Yeah, sure. Go ahead. Is it okay to, for any question on before I answer that? Are there any question on quick find, or I'm going to close this. I'm going to stop sharing. Okay. Yeah. Go ahead.
Is it alright if we could look at the code for heap sort?
For heap sort, is it the code that I sent you?
Actually, I can share my screen since I'm already there.
You're going to show your code, right? You're not going to show your answers to anything, right?
Oh yeah, I'm going to show the code that you posted.
Okay. Well, actually, I haven't posted it. I just mailed it to you. Okay, but yeah, let's look at it. Let me change the security. I mean, I could open it up too, but let's look at this. Let's here. I'm going to change the.
Okay.
I'm going to change it so you can share the screen.
All right.
That code's a little sophisticated. There's some things about generics and I haven't really talked about it. The algorithm itself is pretty straightforward, but there's a couple of steps in there about generics that aren't so obvious.
Yeah.
And if you want me to share, let me know.
Yeah, can you share, please? I'm having a little trouble.
Okay, so just give me a second here, and I'm going to have to open up my. Oh, hold on, students, while I open up Eclipse. Okay, hold on. I'm just trying to find my laptop is a mess here. Okay, so I'm opening up Eclipse, and then as soon as I open that up, I will as soon as it's open up, I'll share the screen. And pretty much it's the code that's in the file. It's a remarkably simple code for what it does. So yeah, Eclipse sometimes takes a while. Okay, so here I think it opened up right to the code that I wanted. Okay, so here let me share this. Hello, let me share this screen with you, and then okay, so here's some code. I know I had implemented this. So can't remember the last time I posted online, but actually, so you had asked about this. So actually, what I did is I actually went back to the Sedgwick website because I think I had my version is maybe I did it when I used to work with NetBeans. I couldn't really find my older code, so I went to Sedgwick website and just kind of took this code and I modified it a little bit so we could use it. So kind of there's something simplified about it in that allows a heap of up to 100. I mean, I could easily modify that, so I could change this to, but I kind of hardwired it, so it's good for up to 100 keys. What's
But
your
before,
question?
but before you go on, I wanted to look at the heap sort code that you had on the priority queue lecture.
Oh, oh, wait a minute. Okay, so this may not do the sorting. This actually forms the heap. So I might have sent you the wrong code. I might not sure I have that available.
Well, I still wanted to see this code, but I still had questions on the lecture notes that I just wanted to go over.
Okay,
with
so
you.
why don't I open up, can I open up the lecture notes and then answer it that way?
Yes.
Okay, so hold on here. You're really testing my organizational skill. So I'm gonna stop sharing while I look for the, I might just open up, let's see if I can't, I might just open up Canvas and then just download it or open it up from there. Okay, so yeah, I'd like to open it up. Let me just download it from Canvas. It might be a fast way for me to find this. Okay, so I'm just going to download the notes from Canvas. Oh, I don't like that. Okay, so hold on here, and I'm going to. Oh, here it is. And I'm going to open this up. And one day this will open up. Oh, here it is. So share screen. And then, hold on. Did I share the screen? Wait a minute. Did I share the screen? No. Okay, so let me do this. So share. Okay, so here it is. So here are the notes. And yeah, so the sorting part, so you got a question on the sorting part. The sorting part all depends on this deleting the max. And so we only did one. So it's actually kind of a long, to actually kind of trace through it, if I like did it on a test, you'd be drawing tree after tree after tree after tree. So so I didn't really want to, just like, actually doing a complete sort with quick sort. It's a lot of, I mean, there's a lot of exchanges just to put one element in the proper place and then you break the array up in half. And I mean, if I actually asked you to sort that whole thing, I mean, I would have a very hard time grading because it'd be just so many steps. And I think you inevitably would make mistakes. It's very tedious. Okay, so let's get to okay, so most of this code was about actually creating a max heap. So remember, so what the max heap does, if you remember, is there any question about how to create the max heap?
I'm good on that.
Okay, so the one thing we know about the max heap, even if you don't know anything about how to create the max heap, is that first of all, you have to know about these syncing operations where, so remember that every parent has to be greater than or equal to its two children. If it's not, you move down. You exchange with the larger of the two children. Okay, so here's where we okay, so then we learned how to, let's say we wanted to do sort example, which is clearly an unsorted array, right? S-O-R-T, it's not sorted. E is less than T and A is less than X. And okay, so it's not sorted. Okay, so remember what you do is, okay, so what you do, so what we do in this example here, so first, like, the array is sort example. It's an array, it's a sequence of those, it's an array of those keys here. Okay, so first we actually have to form, we have to convert what it's called heap. So I don't think Sedgwick uses this term. I know other, like online, they use this term. You have to heapify sort example, because right now that's not a max heap, right? Because like R is not greater than X, and O is not greater than T, right? And E is not greater than L. So what we're going to do is heapify. And so you do it from the bottom up. So you start with heaps with 3 elements and you heapify that. You go bottom up. So we start at element, here there's 11 keys in this tree. You start at position n over 2, which is 5. And then and then you go, and so we actually heap, so I'm going to just draw right on here. I'm going to use red.
You mind if I just ask some quick questions before you continue?
Yeah, sure.
So for the heap sort code, which is I think on the penultimate slide.
I think I might just to actually have the code there. I just described the algorithm. Let me take a
Yeah.
look. But the
Yeah, you
idea
have-
is, let me just say something. So you'd heapify here. So first you'd actually have to heapify. So you would sync E down, and then you would sync. So basically you sync 4, and then you sync 3, sync 2, and you sync 1. And when you're done with that, you will get a max heap. So just take, you either can just take my word for that right now. Okay, so this is actually the code. Oh yeah, you're right. I do have it right here. Okay, so you're right. I do have it right here. Okay, so this is the part. So this is the part right here that actually does that heapifying. Okay, and then you actually sort, and then
that when you called sync there, you just modified it a little bit where you
oh, this is
have
actually,
three.
you know what? I just noticed there's a type that should be sync. I'm sorry, this should be sync also.
Okay, so the difference is just that these have 3 parameters, but it's basically the same. It's essentially the same as the.
Right.
Okay.
But the idea is actually in the, but the thing here is what would happen here is that, so do you notice right here, we actually have a heapified array. So it's actually a max heap, right? And so, and your n is 11, is that right? I think your n is 11. So the array, because remember, it's all being stored in an array. And so our array initially looks like, so 0 is unfilled, and then it's S, the biggest value is always at position 1. And then it's O, R, T, and then L, X, A, and then M, and then P, and then 2 E's, right? And that's position 11. So your N is 11. See, they're actually, the array might be much bigger than N, right? But it's positions 1 through N that are considered part of the heap. And so then what you do in the array is you're going to exchange, right? You exchange S, and you exchange the first and the last value, right? So you'd exchange the first and the last value, and then so you exchange the E and 11, and and see what happens here is that here, I'll just see that E that was an 11 and the S is that, so that S is at, now, see the S is now in its proper place, right? S is the biggest one. The parent, the very top node is always the largest value. Okay, so you exchange what's in the very last position, what's in position N, which is in this case is that E. That E is now at position 1, and now what happens is you ORT, everything else stays the same. And then there's that E there. And then, but the key is you decrease N by 1, right? So N is now going to be 10. So it's only going to be this part of the array. See that S is no longer considered part of the heap. It's in the array, but it's not considered part of the heap. And so what you have to do now is when you did that exchange, let's see if I can move this. Let's see if I can draw it on this one page here. You have this new heap. This is what I'm saying. This is actually some of you, I think it was like in question 3 in the quiz or in the like the handouts. You have this new, now it's only going to have 10 values, EOR, T. Let me just erase it so I have room. So initially N was 11, now it's 10, TL, right? And then it's X, and then it's A, and then it's M, and then it's P, and then it's E. See, there is that S there, but S is not actually considered part of the heap. But see, this is not a max heap anymore, right? Because E is less than R and E is less than O. So what you have to do is you have to sink E down and put it in its proper place. Okay, so I'm going to do that. I hope you don't mind if I'm just going to erase this. And what would happen is you would exchange the E with the bigger of the 2 children, which is R. So you'd exchange E and R, right? And then, oh, wait a second, what happened here? So I did something wrong here. So TL, Oh, wait, so this is, I apologize. So this is not heapified. This is step one. I apologize. Okay,
This
let's,
is the
I might
X.
have to open the worksheet up. I thought that was heapified. I apologize. So that is not heapified. Okay, great. Okay, so let's, I didn't heapify it in these notes here. So sorry, students. Let me go back. Let's look at the worksheet. Let's look at the worksheet and then I can do this. So if you don't mind being patient, and I will, and if anyone wants to go, I understand, that's fine. I thought I was dealing with, I wasn't paying attention. That wasn't heapified. So let me just get the worksheet. So let's just, let me look at a solution file, which is all kind of nicely done here. So I'm gonna, let's just download like the quiz that I posted from last semester. So I'm gonna download this. And let's see, so let's go to downloads. Okay, so now I'm gonna open this back up again. Okay, so I'm gonna share the screen again, and now I'm gonna share the screen. Okay, so here's this quiz 11. This should be kind of the nice type solution. Okay, so draw the heap. Okay, so this is the max. Okay, so what happens here? Okay, so we actually have this heap here. Okay, so sorry, it's over 2. That's great. It's over 2. But this is actually a max. What letter is that? Is that a U? Am I printing this? Yeah, so this is a U, students, right here. This is a U, I guess. That was a U. Okay, so that's a U. I wonder if I can. I don't think I can erase that. Yeah, okay. So that's a U. Okay, so what does the array look like now? So and what is our n? Our n is 9. Okay, so we had these keys here. We had a bunch of keys, dk, whatever, right here. And we formed it and we heapified it. No, this is actually inserting keys one by one. We inserted the keys one by one. Okay, and so we came up with this heap right here. So so the largest value is always in position 1. Oh, why is it doing that to me? Oh, it doesn't like me. Okay, so let's see if I can. Let me go down a little bit in terms of size, font size. Okay. So what do we have here? Let's see, it'll. Okay, so the 0 is not filled in. So it's W, U, S, K, F, G, D, and there's another D, and then there's an E. Okay, so that W is the absolute largest value, and N is 9, right? Okay, so then what are we going to do? So now what you do is you actually exchange W and E, and you subtract 1 from N. So what would the array look like? That E is going to be a position 1, right? It's going to correspond to this tree right here. So nothing at 0. E, there's that E at position N, position 9. So E, U, S, K, F, G, and then D, D, and then that W is still going to be there. D, D. See if I can get this W in here. But the W is just not going to be considered part of the heap. So only this part is considered part of the heap, right? And so clearly this is not a max heap, right? This is not a max heap because E is bigger, E is less than U, and E is less than S. So you have to sink it down. Okay, so you sink it down by what happens? You exchange U and E, and then you exchange E and U, and then E and K, and you come up with this. Okay, so now your array looks like this. Now the second biggest one is now in position 1.
And for the sorting, you only want us to show the final tree?
But you're not actually sorting, you're just doing one step, right? You're just, yeah, all you'd have to do is something like this. I'm not asking you to show the arrays. But I'm just showing this is how it sorts though, right? So only this part right here is considered part of the heap. So now let's say I want to do the next, I didn't actually do this in class the other day. Let's say I wanted to do the next step of the sorting algorithm. Because no one actually, I don't think people use this to sort. I think they use merge sort or quick sort. Okay, but let's say I wanted to do one more step of this. What I would do is you always exchange. So now your n is considered, what is it? 4, it's 8. So your n is 8. So your n is now 8. So that w is no longer considered part of the heap. So you'd exchange u and d. So you would exchange u and d. D, K, S, E, F, G, D, that's a D. And now the last two are U and W. See, these last two are the two biggest ones. And you said now you make n equal to 7. So only this part is considered part of the heap. And then you'd have to heapify that because D is not greater than K or S. So what you do is you always exchange what's in position n and position 1, and then you do a syncing operation. And then the next step, so you're always exchanging what's in position 1 and position n. So you're always taking the biggest one, the next biggest one, and putting it in position n. And that's how it sorts. Does that help a little bit, Dominic? You just do that over and over again. And each time, the number of elements considered part of the heap decreases by 1. So the tree gets smaller and smaller.
Yes, it helps.
So I don't ask students to, that's what I'm saying, to actually do this. If I actually showed you, if I actually just sort this whole thing, you know, I mean, just think how, just like even a small tree, let's say 5, just think how many steps that would take. So I already asked you to do 1, and maybe I should go into a little more detail so you can really understand the sorting. But that's what happens. And I will get I can get the code probably tomorrow for the actual sorting, the code that actually does the sorting. But are there any questions right now, or?
Yeah, thanks for going over it.
Did you get all your questions answered, Dominic?
Yeah, it was really just over the code, you know, like
Okay.
like you saw that instead of saying calling sync, you called size.
Yeah, okay. Yeah, I just noticed it when I was talking. I'll see if I can find the notes and figure. I'll just handwrite over it. And I'll get the code tomorrow, the actual code tomorrow.
For sure, but it's all good.
Okay. Okay. Anybody else?
Thanks.
Yeah.
Oh, thank you.
Okay. Okay. I'll talk to him. Yeah, I'll just stay here until everyone's gone. I'm going to stop
Thank you.
recording though.